In this video, we're going to take a look at the formal definition for a limit where both x and y are getting big. So they're both going to either infinity or to negative infinity. So again, I've still got up on the board our basic model for the formal definition of a limit. And now I want to take a look at the limit as x goes to infinity of f of x being negative infinity. So as we're going really far to the right, we're going really far down. And I've got an example of that graphed up here on the board. Now, obviously, there are variations on this. X could be going to infinity or negative infinity, and the limit could be positive or negative infinity. I'm not going to write out all 4 different variations. You're responsible for all of them. But the basic idea is you just modify things depending on whether you're getting big and positive or big and negative. All right. So this is going to mean basically that for every blank, there's a blank. Such that if blank is true, then blank is true. Now this time, since both variables are going to plus or minus infinity, none of the blanks are going to match my basic model, because the basic model is when both variables are approaching a finite number. Here, they're both getting big. Okay. But it's still going to be the case that I'm going to start and end by talking about my y values. And what I'm claiming about my y values is that they get big and negative. So I'm going to need to introduce a standard of bigness in the negative direction. So I'm going to say for every m less than 0. So I'm going to introduce a negative number, m, and we're going to view that as our standard of bigness in the negative direction. So that we'll say our y values are big and negative if they're below this line. So that's what we're trying to get to, that f of x is less than m, that it's below that line. So big in the negative direction. Okay. And what makes that happen? Well, that happens as x is going off to infinity. So we're going to need to introduce a standard of bigness for x, and this is in the positive direction. So we're going to say, well, let's see, it looks like once we pass this point right here, which I'm just going to call n, if we go to the right there, we're going to just keep going right and down, so we're going to be below this standard of bigness for y. So there's an n, which is a positive number, because it's a standard of bigness in the positive direction, so that if x is bigger than n, if we go to the right of n, f of x will be smaller than m. Then f of x will be big in the negative direction. Okay. Again, I'm not super concerned that you use m for the y's and n's for the x's. That's what our book does, so I'm going to try to be consistent there. But it's not as standard as the epsilons and deltas are. What is important is that you've got to have two different letters. You can't use the same standard of bigness for the x and the y values. So one letter to be your standard of bigness for the x's, a different letter to be your standard of bigness for the y's. That's really important in this case because this is a negative number and this one is a positive number because one variable was going to plus infinity and the other to minus infinity. But even if they're both going to the same signed infinity, you still need to have different standards of bigness for the x and for the y.